Sorry, yesterday it was a relatively abstract, but a little bit also formal lecture with many home, 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 R home, R home, R home. Today you will have gamma, 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 R gamma, R gamma, R gamma, basically. But there will be some explicit, there will be something happening. Today we actually have some analytic arguments and stuff like that. So geometric string theory is unfortunately a rather technical subject. And so I have to make a choice. Either I want to give all definitions of all these things and then basically I just spend the lecture doing nothing. Or I just pretend that you know the Proital site of an adic space and then we play with that. If you don't know what the Proital site of an adic space and the corresponding sheaves there, don't worry. Just think of the étale site and the structure sheaf and you will still get a grasp of what's going on. But I really don't want to go into all the preliminaries about Proital site because otherwise I would basically do nothing today. So as I said, this started really with Sen. Well, actually it started with Tate and Serre. And it was really about representations of the Galois group of QP or some finite extension of it. So if you take C to be CP, the completion of an algebraic closure of QP, and if you take V, a finite dimensional continuous representation of of the Galois group of QP over QP, one thing which you can do is to consider the base change to C endowed with the diagonal Galois action. And this becomes a semi-linear C representation of the Galois group. But now it turns out that such representations are equivalent to just giving QP cyclotomic semi-linear representations of a much simpler group, which is gamma, the Galois group of QP of mu p infinity over QP, which is ZP star. And so this is now a p-adic Lie group, which is commutative of dimension 1. And the functor is very, by the way, so this QP cyclotomic is really the completion, and this is crucial, is the completion of the extension of QP obtained by adding all p power roots of unity. And this is one of the typical examples of perfectoid fields. And actually, this equivalence of categories, you can think of it nowadays in terms of almost purity, but it was already almost purity at that time, okay? And the functor here is simply you take a representation W and you take the invariance under H, where H is the Galois group of QP bar over QP of mu p infinity. And it's precisely the perfected nature of this field which in some sense makes the Galois cohomology of this group trivial, and so this gives you an equivalence of categories. But there is one very subtle story, is trying to descend from this perfectoid field to something which really lives over QP of mu p infinity. And this is actually the most subtle part in the story. And this is a decompletion process which is essentially Sen theory. And this is really not obvious if you read the letters between Serre and Tate. There is a question that Serre asked at some moment: if you take invariance of C under the Galois group, do you get QP? And then they start exchanging, and Serre says at some moment, okay, this should be trivial, but the more I think about this problem, the more I don't see how to attack it. So this is really not an obvious statement. And so already for the trivial representations, these things are not obvious. Well, I mean, nowadays, of course, we know how to do them, but a priori, when you see this for the first time, it's not something that you just start writing down things and you end up with QP. And so in this decompletion process, what you do is to define d sen of W to be simply the space of vectors which are gamma finite, in other words, those W and W, such that the orbit under the action of the group is finite dimensional. This was Sen's original definition. And then you show, and this is the non-trivial part, that this has the same dimension. A priori, it's not even clear that this is non-zero. Okay? But you prove that this Sen is big enough to actually generate the representation. And so you kind of manage now to get a finite dimensional vector space over this guy, and this still inherits an action of gamma. It's obviously stable under the action of gamma. But now the great advantage is that you work over this thing, which is somewhat relatively small, in the sense that this finite dimensional vector space will actually descend to a finite dimensional vector space over QP of mu p to the n for some n. And there, you know that finite dimensional representations of p-adic Lie groups are automatically locally analytic. And so this is locally analytic, but this is also kind of obvious just because I impose the condition on the orbit. Is any semi-linear representation of finite dimensional, of course. So all my representations are finite dimensional and continuous. Maybe I should say, yeah, this is kind of implicit. Everywhere we put topology on this and we impose continuity. And so for any such W, which is the same as a C semi-linear representation of the absolute Galois group, this descent is big enough. And this action is locally analytic. So yeah, I realized that I managed to give a lecture on locally analytic representations without ever mentioning the action of the Lie algebra, which is a great performance. Yeah, I don't think anyone has ever done this. So you talk about derived solid representations, but you never know that basically the reason for which you introduce those is precisely because you want to differentiate the action of the Lie group on the locally analytic vectors, and that you cannot do on the original representation. Yeah, but I was thinking that this is kind of obvious, but okay, apparently one has to spell down obvious things very often. So differentiates and gives an action of the Lie of gamma on this Dsen. But Lie of gamma is just QP, right? So to give an action of this Lie algebra on this is just give an endomorphism. An endomorphism, theta sen W of Dsen of W, which is actually linear over this. And so via this isomorphism, I can just base change this endomorphism. I get a QP cyclotomic linear endomorphism of W. Which is called the Sen operator. Okay? So this is an extremely nice construction which works for Galois representations. But basically today we are interested in the geometric aspect, not in the arithmetic one. And so we're not going to work over a geometric point like this and study the pi 1 of, I don't know, spa QP or something like that. But rather we're going to be interested in representations of the fundamental group of some affinoid, for instance. And then this QP cyclotomic is going to be replaced by certain perfectoid algebras that are cooked out from that affinoid. But still, this is a picture to keep in mind. One of the first things to do is to see your V as some local system on the arithmetic point, extend scalars to C, which essentially comes down to taking tensor product with the completed structure sheaf of the Pro-Étale site, and then you have this descent to the somewhat abelian perfectoid extension, and then some decompletion process. And this is basically what I want to explain now in the relative setting. So let's study, so let me call this killing or locally analytic vectors in the case where gamma is just a p-adic Lie group, which is commutative, so just, let's say, NP torsion free, so a bunch of copies of ZP. The whole story is actually very interesting already for d equals 1. And essentially most of the arguments in, so here I'm talking really about Camargo's paper on geometric Sen theory. Most most of the arguments reduced by induction to the case d equals 1 in the end. But one has to be careful. One has to set up the theory in sufficient flexibility to allow inductive arguments. And this is why when you read his paper, you will see that he starts in a very general context, and only at the end he specializes to the case that I'm interested in now. But of course, to save time, I'm just doing the opposite thing. So, yes? Well, because you see, if I take a vector in there, the span is finite dimensional. Okay, so I have a finite dimensional representation of a p-adic Lie group, and it's a general result of Cartan that this is all automatically locally analytic. Yeah, so let's consider the following setting. I'm going to call this the small setting because it's going to occur all the time in this lecture. So we're going to take C, I'm going to keep it CP, but actually any perfectoid field over QP cyclotomic would work. And I'm going to let TD be the d-dimensional torus, which is really a circle, actually. Okay, so this is an affinoid adic space, and now I'm going to look at a nice cover, a proital cover of this, which is some analog, geometric analog of this QP cyclotomic, which is obtained. Well, there, what did I do? I took one and I extracted p power roots. Here, I take the coordinates and I extract p power roots of all of them. And this turns out to be, I mean, this is like the standard example of a perfectoid C algebra, which plays the role of QP cyclotomic in the above picture. But I'm going to do something slightly more general than simply this setup, because I'm going to take X, an affinoid, which, well, I'm just going to call this is the standard name for these things. This is a toric chart. In other words, a finite composition of rational localizations and finite étale maps. Just think of the case of you take an open rational subspace in TD, or you take a finite étale cover of such a thing. Okay, so this is the small setting in the sense that this X has some preferred coordinates given by these TIs pulled back from TD. Well, this TD infinity over TD is a proital torsor for gamma, which is ZP of 1 to the D, where ZP of 1 is mu P infinity, and I'm always going to identify it with ZP via a choice of P power roots of unity, compatible P power roots of unity. Okay, so this is just ZP to the D. And it acts on the coordinates as you imagine. So when I have a proital torsor for a group and I have a space over this, I can just base change. And so I'm going to call this pa A infinity, A plus infinity, where this is still a perfectoid algebra. And this is actually now a highly non-trivial fact, which follows from almost purity theorem. But again, you can just assume, if you don't want to spend too much time on this, just assume that X is the torus, in which case this A infinity is given by this very explicit perfectoid algebra. And so it's really this A infinity which is going to be the analog in that picture of QP cyclotomic. Okay, so now we need some V like that, which is some sort of local system on X. But actually, for the applications to locally analytic vectors, it is very important to consider much more than just finite dimensional local systems. So we're going to consider a certain class of sheaves which are essentially some Banach O-hat modules which are orthonormalizable and which have nice lattices. So definition, an O-hat X module, so this is the completed structure sheaf on the parietal side of XF, is called small. Well, Rodriguez Camargo has a very long name for such things, but okay, to save time, let's call it small. So is small if et al. Locally on X, it has a p-adically complete O hat plus X lattice. So you can think of this as the sheaf of functions bounded by 1, F plus. So F is just F plus when I invert P, such that the special fiber of this F plus, mod P, is almost isomorphic. Again, you can safely ignore the almost, to just an infinite direct, or not necessarily infinite, I mean a direct sum of copies of O plus mod P. In other words, as an O plus mod P almost module, this is really free. Okay? But we do not ask that I is finite, so maybe infinite. So this is this looks very much like the crucial example of locally analytic Banach representations that I gave yesterday. The criterion for local analyticity in a Banach representation was precisely you have a lattice which is preserved by an open subgroup, and you ask that the special fiber, in some sense, is kind of trivial. So, and typically, so two key examples of small sheaves. I mean, this is clearly a definition which makes sense for any adic space. I don't need it in this setting, right? But two key examples are finite locally free O hat X modules are small, but this is actually already not trivial. This is due to Kedlaya and Lue. And really the key example, and it's a construction that is going to come all over this lecture, is the following. You take X tilde goes to X, a parietal G torsor, where G is a compact p-adic Lie group. So this will be the setting coming from towers of Shimura varieties, and I will discuss the setting very seriously or not at the end of the lecture. But so far, this is just an abstract setting. You take any parietal torsor for a compact p-adic Lie group, and then you take V, a locally analytic QP Banach representation of my group G. Now, when I have this, I can always consider a sheaf V underline on X tilde, which is morally the constant sheaf V, except that, of course, it's not really that, because you have to take into account the topology on V. But morally, it sends U to continuous functions from the topological space of U into V. And this makes sense because I have a topology on V. And one of the nice features of this parietal site is that it allows you to make such constructions. So I have a sort of constant sheaf here, and then there is a classical construction of descending a sheaf along a torsor. Okay? So if I call this map pi, I get a sheaf which I'm going to call V parietal, which is just I take the push forward by pi, and then I take the invariance under the group G. And this is a QP sheaf on X pro etal. Okay? So again, any locally analytic Banach representation of the group will give rise to a certain sort of local system on X, a pro etal local system, except that V has no reason to be finite dimensional, and so this local system does not have finite dimensional fibers. But still, this construction makes sense. And so I will define. Can
you explain why the first example is not
It's not so clear that, I mean, yeah, because here you ask triviality pro etal locally. So your guy becomes free only on some pro etal cover, but here you ask locally etal for the etal topology. Okay? So it's not obvious that if you have a lattice over an enormous cover of your space that you can get one locally for the etal topology.
So it's hidden in your definition of locally in both cases?
Yes. Yeah. I mean, here it's locally for the etal topology, etal locally, and here it's locally for the pro etal topology. And these two are not the same. But one of the key properties that Kedlaya and Lue prove is that on a perfectoid space, these vector bundles for O hat are already trivial for the analytic topology. This is false, of course, for rigid spaces. But then there is some descent argument which allows you to deduce this. OK, so the key player for us will be the sheaf V pro etal, completed tensor product with simply the structure sheaf of X. So this will be an O hat module on X pro etal. And here's an exercise. This is small. This is much easier to do than this Kedlaya-Lue thing. And precisely you can guess what's the key ingredient, namely the triviality of V mod P of a lattice in V modulo P. And then you can perform exactly the same construction to get a lattice, starting with a lattice stable by G, for instance. In V, you can do exactly the same construction with that lattice, and that will give you some lattice in your FV. And then essentially the fact that the action of G on that lattice mod P is trivial will tell you that when you reduce the corresponding FV plus mod P, you just get a direct sum of copies of O plus mod P. So this is really a simple exercise, but it's a crucial example which goes far beyond just vector bundles. Now, a typical example to keep in mind is the following. You take V to be C HLA of G. So these are functions with a given analyticity radius. So as we saw yesterday, this is a typical example of a Banach locally analytic representation. And so, well, let me call this VH because it clearly depends on age. And I could consider the sheaf FCLA of G, which is by definition the colimit over age of these sheaves. And now let's see what's the link between the pro etal cohomology of this guy and locally analytic vectors. No, this is not small. Because, I mean, these lattices kind of vary. But it doesn't matter. It's just some O hat module. And the cohomology of that O hat module is just the colimit of the cohomologies. And so you can still have a good control on those. OK, so now let's try to compute our gamma. I'm going to, so everything is pro etal here. Of X into this FCLA. This is what? Well, since X is QCQS, this is the colimit of our gamma XH FCHLA. Oh, sorry, this is X. But now I can use Hochschild-Serre, or maybe descent if you want, along the torsor X tilde goes to X. This is the colimit of R gamma G, and then R gamma X tilde F CHLA restricted to X tilde. But how did I define this sheaf? Well, I had this local system coming from V, which was constant on X tilde. and then I tensored with O hat. So, and I descended it along this torsor. But now if I still restrict it back to X tilde, I just get V underline tensor with O hat. So this is the colimit over H of R gamma G, R gamma X tilde, O hat X restricted to X tilde tensor with CHLA. Okay, so this looks like a complete mess, but at least if we are in degree 0, you check that this is nothing. But so what happens here? There's nothing happening, so it's just H0 of G, H0 X tilde with this guy. But this is just you take the functions on X tilde, and then you tensor, completed tensor product with CHLA. So this is just, you take O of X tilde, which I'm going to denote by A tilde, and then you completed tensor product with CLA, and invariant under G. Oh, guess what? This is exactly the locally analytic vectors in A tilde. So you see this geometric construction allows you to study locally analytic vectors in the functions on X tilde by expressing them as Proetal cohomology in degree 0 of a certain, well, clearly very complicated sheaf. But still, it's the kind of sheaf we're going to study and for which we can develop some Sen theory. So the whole purpose of Sen theory now will be to study the Proetal cohomology of such small sheaves and develop some tools to control these cohomology groups. Okay? And then you basically apply that knowledge about the cohomology of such sheaves to this very specific case to get information about the locally analytic vectors in A tilde. There is one subtle point. Things are more complicated with higher locally analytic vectors. And let me tell you in a second why. If X tilde was affinoid perfectoid, then basically here you can switch this cohomology and tensor product with this guy. You can take out the constant Banach representation, and here this is concentrated in degree 0. So if X tilde is perfectoid by almost purity, you have such a statement even for higher locally analytic vectors. And this is precisely the setup in which Lue Pan is doing his work, where he knows that the perfectoid modular curve is, that the infinite level modular curve is perfectoid, and then you're kind of saved in this setting. But if you work with arbitrary Shimura varieties like Camargo does, then this is absolutely not known, and so this is a very serious problem. Okay? So if X tilde is affinoid perfectoid, almost purity implies that R gamma X tilde O hat tensor with CHLA is R gamma X tilde O hat. It's very easy to say nonsense with these things because, of course, you would like to say, oh, this is an orthonormalizable Banach space, so this is like a completed direct sum of copies of O hat. I could just take it out. But, of course, in this completed tensor product, you see the cohomology of O plus, and for the cohomology of O plus, that's a very complicated thing. But except if you are in a setting where you have affinoid perfectoid space, and there you know that everything is almost acyclic, and then you kind of can exchange limits, colimits, and whatever. So this holds in that case, and moreover, this is nothing but the functions on X tilde completed tensor product with CHLA, and so the cohomology of X F CLA really is the higher derived, the whole derived locally analytic vectors in A tilde. Okay? But if not, it's more complicated. Okay. So this was basically to try to explain why we are interested in the study of the Preutal cohomology of such small sheaves, because it kind of includes the study of locally analytic vectors in functions on Preutal torsors over a given small adic space. So now let's come back to the general setting, small setup, so in which I have toric coordinates. And let's construct Higgs bundles and Preutal cohomology. So now this will be a construction which is supposed to imitate the construction of the Sen operator. So this Sen operator was just some endomorphism of some vector space. Now, of course, if you are in dimension 1, Higgs bundle are nothing. It's just endomorphisms of your vector space. But if you are in a higher dimension, then things get more complicated. But the basic idea will be kind of the same thing. We're going to start with a small sheaf F, construct out of it some funny locally analytic representation, or not really locally analytic, but solid representation of gamma, do some decompletion on that, and construct out of that some endomorphisms, or Higgs bundles, which kind of correspond to an infinitesimal action of gamma. So, of course, this is a little bit technical. So let's start with some abstract Sen decompletion. So this will be a very general result, very similar to what Sen proved there, in this setting of adic spaces with toric coordinates. So we keep our X goes to TD. And so from here we have the ring A infinity, which is a perfectoid algebra. And so we're going to be interested in semi-linear representation of gamma, which I remind you is just Zp to the D. So this is A infinity semi-linear. So the coefficients are now A infinity, not QP cyclotomic, or versions of that. And which we're going to assume that is small. So I have to tell you what it means to be small for such a representation. So I have just a semi-linear Banach A infinity module with an action of gamma. And again, it will be some sort of triviality of the special fiber, but it's a lot more subtle than this. So what does it mean? It means that there exists gamma prime in gamma, which is open, but you may safely assume that it's just gamma. And an A plus infinity submodule, V plus inside V, which is p-adically complete, which is a lattice in V. So far it's very similar to the above setting of small sheaves. And we're going to ask something about the reduction mod P. And A plus mod P, V plus mod P, is a free A plus infinity mod P module having some basis fixed by gamma prime. Now, be careful because this definition is a lot more subtle than you expect. And I discovered this last evening. So, because he introduces a complicated notion of relative locally analytic representation, and then you kind of think that this V is a locally analytic representation of gamma. This is not the case. So, okay, gamma is a compact p-adic Lie group. This V is a Banach space. So what would be the condition that it's locally analytic? You should have a lattice whose reduction mod P is fixed by gamma prime. But here you don't ask that the reduction is fixed by gamma prime, only that the elements of some basis are fixed. Now I remind you that this gamma prime does not act trivially on A plus infinity mod P. Okay? So the fact that this module has a basis which is fixed by a gamma prime does not imply that V plus mod P itself is fixed by gamma prime. And so this V is not necessarily a locally analytic representation of gamma. Here's a key example to keep in mind of Small's representation. You take W Banach locally analytic representation of gamma, and then you do W completed tensor product over QP with A infinity. This is small. But it is not locally analytic with respect to the action of gamma. Aha. So, remark, no, it's very far from being that. Namely, if you take even the derived locally analytic vectors, these are just concentrated in degree 0, and they are just given by the smooth vectors. Okay. So there are really not many locally analytic vectors in this A infinity. Only the smooth ones. Exactly the same setting happens in the case of QP cyclotomic. If you take QP cyclotomic and you look at gamma locally analytic vectors in there, you just get QP of mu P infinity. Okay. It's related to the it's precisely related to the fact that the action of gamma on A infinity itself is not locally analytic. Yeah, exactly. Yeah, yeah. Okay, so now here's the theorem. But I really want to emphasize that this is really Berger-Kolmez and Sen. Well, actually, Sen and Berger-Kolmez and Kolmez. I mean, Sen did this in that very specific case, but the method was sufficiently flexible. And then Kolmez kind of made this very abstract formalism of Sen decompletion. Then this was further extended in work of Berger-Kolmez, and Camargo goes even further because in this work of Berger-Kolmez, they only work with finite free modules over A infinity, while here you allow orthonormalizable A infinity modules plus some extra hypothesis, but still you are not in the case of finite free modules. However, the method in this paper is sufficiently flexible so that if you put this hypothesis here, you can just carry on the whole argument in exactly the same way. So that's why I'm putting all these people. So you take such V. Well, as I said, this is not necessarily locally analytic, but the theorem will say that it has many locally analytic vectors. In the example of QP cyclotomic, as I said, the locally analytic vectors are QP of mu P infinity, and that is still dense in QP cyclotomic. So then there exists a H, which is big enough, such that if I look at locally analytic vectors of radius H, this is an orthonormalizable Banach AH locally analytic modules. So this AH-LA is some Banach algebra, but which really comes from finite levels. And the natural map and kind of generates your module. With respect to the action of A infinity. Okay, so it's exactly the same sort of statement as in the theorem of Sen. And moreover, this will be a generalization of this example here. If you take the derived vectors with respect, the locally analytic vectors with respect to the action of gamma in derived sense, this is concentrated in degree 0 and is just given by the colimit over n. And here you have to be careful. So you have to take A fixed by P to the n gamma, completed tensor product with A infinity. I keep forgetting about this infinity thing. With V HLA. So one really has to be careful with the order of colimits and the completed tensor product here. So it's not really the smooth vectors. It's so if V is the trivial representation, if not, is given by this funny colimit of completed tensor products. Okay, so that's what the general decompletion formalism gives you, and it's, of course, just as difficult as that one, plus an extra layer of technicalities related to the fact that you are in arbitrary dimensions, so there is a reduction to the case d equals 1, where all the work is happening. And for d equals 1, you just have to go through all the formalism again of Sen and do the decompletion process. So it's a joy in killing co-cycles, and you have to work with 3 or 4 there is, such that for all, there is, such that for all, and so on. So of course, it's not something that you can do on the board. Okay, so that's something that we're going to take for granted, but now I have to tell you how you construct a Sen operator in this setting, but it's kind of obvious now because you just copy the construction there. You have an action of the Lie of gamma on this. That action is going to be linear with respect to this, because these are smoothed with respect to the action of gamma. And so you can just base change, and you get an A infinity linear operator on V for each element in the Lie algebra of gamma, and that will, you put them together, and it gives you a Higgs field. So let me write this. So Lie gamma acts on V age LA, A infinity age LA linearly. And so this gives a map, well, I'm going to call Sen V, I guess, from Lie gamma tensor QP V into V, or dually theta V into the Lie of gamma dual tensor QP V. And this is a Higgs field. Well, this is just basically saying that the corresponding endomorphisms that you get commute, and this is simply because the Lie algebra itself is commutative. Okay. So each element in the Lie algebra will give you an endomorphism of V, basically, and saying that it's a Higgs field is just saying that those endomorphisms commute, but this is obvious because, I mean, this is a commutative Lie algebra. Now, there is a standard construction which allows you to extend this to a complex. Yes? Yeah, I fix once and for all such an age, okay? And the colimit will be independent of the choice of age. This is not the same as the smooth vectors in V. Yeah, but you take this guy and you take completed tensor product with this huge thing, okay? So if it was just an, how to say, algebraic tensor product, then this would be smooth. But this is a completed tensor product at each step, and then you take a colimit. Well, it's the same as the solid, but okay, today I'm having enough of putting boxes. And okay, and these are really Banach spaces, so let's be serious. So far, because at some moment you have to put boxes when you do with R gamma and so on, but here completed tensor product is more. Actually, these are orthonormalizable, so these are really completed direct sums of free guys. Okay. You can do that, but still it's not going to be a smooth representation of gamma.
No, but
okay, this you can. This you can, sure. But this is just symbolic manipulation. Okay. So from here you get a Higgs complex, which essentially computes, which is the Chevalier-Eilenberg complex computing the Lie algebra cohomology. And then you base change to V. And the theorem, this is actually, you might think that this is obvious, but it's not. And even when you know what is the trig, this is still not obvious. So it says that the cohomology, continuous cohomology of gamma on V is just given by, you take the cohomology of this complex, I don't know how to call it, Higgs of V, I guess, HI of HV, and then you take gamma invariance in there. So this gives you a way to compute cohomology of your group on these small representations in terms of these linear operators of this Higgs field that you constructed out of V. So this is, of course, an extremely interesting calculation because this is very often related to a Proetal cohomology group at the end. And so this allows you to compute the Proetal cohomology that we were interested upstairs, re-express it as something like this, and then it will become just the cohomology of certain Higgs complexes. And in principle, in good situations, you know what the Higgs field looks like, and then it becomes a linear algebra calculation. And here the key input is precisely the comparison that I discussed yesterday between continuous cohomology of V and that of its locally analytic vectors. That's the first step. Now this, as I said, is concentrated in degree 0. But then there is an extra step, which is a comparison between Lie algebra cohomology and locally analytic cohomology, which is proved in basically the same way as the methods that I introduced yesterday. So I don't want to go there. Sorry. R gamma Lie of gamma. This is becoming unreadable. I'm going to rewrite. No, but I'm going to rewrite this because it's kind of small, but not in that meaning. So the general statement is that R gamma V, which holds all the time, so here you really compute cohomology with respect to locally constant cochains, and then here you compute Lie algebra cohomology. This is one of the main interests of these locally analytic vectors, because these continuous cohomology groups are extremely hard to compute in practice. Now, once you linearize the action of the group, very often it becomes a lot simpler, in particular this kind of Higgs complex. And so on this you can get your hands on, and then you still have to take smooth cohomology, but this is essentially taking gamma invariance, and once you have a relatively good understanding of these things, at the end taking gamma invariance is relatively easy. Okay, one of the key points is that smooth group cohomology in characteristic 0 is essentially trivial, right? So, okay, so now that we have this very general result, let's come back to our small sheaves. So now let's sheafify this. It's the Lie algebra cohomology, but you still have to, the Lie algebra only acts on the local analytic vector, so you still have to base change to V. This is why it's a little bit tricky, because this is really what you expect tensor with A infinity, and then you still have to take the gamma invariance there. So yeah, I really got confused a lot at some moment in his paper, because I was thinking, but why do you need this? And okay. No, these things are, they look easy, and then every single time you try to actually understand what's going on, you discover that there is another subtlety appearing. But okay, these are not too hard. Once you know how the SEN method works, you just kind of follow your nose and you prove such things. So now let's try to sort of sheafify this construction. So let's take x to TD, small as usual. And, sorry? There was no question. And F a small sheaf. Now, it turns out that this small sheaf is actually controlled by something very easy. So such F is really determined by one small, or many small here, A infinity semi-linear gamma representation. And in other words, such sheaves will correspond to such representations that we have just discussed. Their cohomology will correspond to the cohomology that we computed here, and then basically you just have to sheafify everything. So why is this the case? So the point, oops, is that O plus mod P is almost a cyclic on on X infinity, which is an affinoid perfectoid space. So this is the almost purity theorem of Faltings and Scholze. And so once you know that the special fiber of your lattice is a direct sum of copies of O plus mod P, so this will imply that F plus mod P itself is almost a cyclic, then you can kind of lift this acyclicity by devisage, and using the fact that F plus is p-adically complete, so this is successive approximation, this will tell you that F itself is a cyclic. Now I'm inverting P, so there is no almost anymore, is really a cyclic on X infinity and determined by its value there, which is f of X infinity. So to put it into simple words, you start with your sheaf F on X, you evaluate it on this perfectoid cover X infinity. There, it's obviously a module over the ring on X infinity, which is A infinity. It still inherits an action of gamma because gamma acts on X infinity. So you end up with a small semi-linear gamma representation, and the restriction of F to X infinity is gamma equivariantly isomorphic just to this V completed tensor product with the structure sheaf restricted to X infinity. And so if you have a sheaf, you know its value on X infinity as a gamma equivariant sheaf, then you know it on X, because X is the quotient of X infinity by gamma. Okay? So such sheaves are completely determined by just their values on these things. I could actually have started by just saying, okay, I'm only interested in sheaves that look like this. But it's a little bit perverse because everything I'm doing here depends on the choice of my toric coordinates. And that's one of the subtle points. I would make a definition which would depend on the choice of the coordinates that I pick on X, and I don't want to do this, okay? But in the end, you can play the game in the opposite direction and still have this. Great, so now, well, you just sheafify those things, so now you get a Higgs field, which is O hat X linear, theta F, from F to F, and now I'm cheating a lot, of course, so I have to tell you where I'm cheating, because a priori there, I just have the dual of the Lie algebra of gamma tensored with my F, so I still have to make an identification in some sort. This is a finite dimensional QP vector space of dimension D, so these are just D copies of V. So I have to give you D endomorphisms of V, while here I'm taking my sheaf and I'm tensoring over A with the differentials of A, but this is again just a finite free module of rank D over A, so this is again D copies of A. A basis of omega 1 A over C is just given by the D log of the coordinates. Okay? So now I have to give you the value. What is this doing? So induced by a similar map from V to the direct sum of V dTi Ti mod minus 1. So now let's see, what can we do? Well, what did we do in the sen setting? We had this D-sen. We differentiated the action of the group gamma on it. This created endomorphisms of that Galois representation or D-sen, and we use those to construct this thing. And we'll do exactly the same thing, but you cannot start with an arbitrary element in V because that's not necessarily gamma locally analytic. So you use this decomposition here. If you want to give an A infinity linear map from V into something, you just have to give an A infinity HLA map from this guy. But now the action of gamma is differentiable on age LA. So this is A infinity hat tensor A age LA V age LA. So I'm just going to send one tensor V, where this is now locally analytic, is going to be sent to the sum of, I'm going to write it this way, partial IV dTi over Ti minus 1, where this is the infinitesimal action of the Zp sitting inside gamma. This is the ith factor on V. Okay, so your gamma is Zp cross Zp cross Zp. For a given I can look at the ith factor in there. That gives me a one-dimensional parameter subgroup in gamma. I take the derivative with respect to that parameter subgroup on my vector, and then I have to renormalize things by this dTi over Ti, and then T-twist by minus 1. And now there is something really amazing here, is that this is actually independent of any choice. Now, as you can see, it highly depends on the choice of the coordinates that I took. And now the really cool part is that this construction is actually independent of the toric coordinates. And well, so far, basically all the proofs I saw are 2 pages of bookkeeping and computations in Galois cohomology. And frankly, I really hope that someone will come up with something better. So this was first observed by Lue Pan in the case in one-dimensional case, and then it was proved by Rodriguez Camargo. But I think Tongmu He has a somewhat cleaner approach for these things, but I'm not competent enough to tell anything about that. So this construction is independent of the toric coordinates. And so it globalizes to any smooth adic space and small O hat X module. And so if I have something like this, that will tell me that the cohomology, if I'm interested, okay, so now this will be a little bit fancy, sorry about that. But this is just a way of computing pro-étale cohomology by projecting from the pro-étale side to the étale side, which is the standard thing people do. So if you are interested in the higher direct images of this projection, in other words, computing cohomology in degree I on the pro-étale side for this sheaf, but locally, this is just the projection of this Higgs complex. Okay, so roughly speaking, we kind of ended our job now because we found a way to compute the pro-étale cohomology of any small sheaf in terms of linear algebraic data. And then it's only on age 0 because this is really not derived at all. You just project it to the étale side. So if you apply cohomology, you are just taking age 0 pro-étale of some of the cohomology of a certain complex of sheaves. So let's go back to our setting that we're interested in, where we take a torsor So now I'm going to consider a pro-étale torsor where this is compact p-adic Lie group. This is small, in particular affinoid. And Well, in this case, as I said, for each Banach locally analytic representation, I get a sheaf FV, which is a small O hat X mod. And so I can apply to it that construction. So I get theta V, an associated Higgs field. But now you would like to say, okay, what happens when I vary these Banach locally analytic representations? Is there some universal operator which allows me, universal Higgs field, which allows me to compute all of these things simultaneously? Now, what you can do is to look at the Lie algebra of the group, and this will act on any such V, right? I mean, as I said, that's what locally analytic representations are made for. And so you can dualize this, and you get a map from V to V tensor, the dual of the Lie algebra. So since the constructions of all these sheaves here are kind of functorial and Tanakian or whatever, this will tell you that you get a map from FV to FV tensor, the dual of this guy. But this is what? This is V tensor G dual pro et al. Tensor with O hat. But this is, now it's symbolic mathematics, you have to rearrange things. So you do G dual tensor with V tensor O hat. But guess what? This is nothing but FV. So you get in this way a map from FV to G dual tensor FV. So the best hope you would have is that you can use this map together with some universal map from G dual to omega 1 tensor O hat to recover all of those things. And that's what he proves. So I want to emphasize that these things actually go quite a bit further than what Lue Pan does in his first paper, in which actually he asks whether all of these constructions can be made functorial, independent of choices, can be globalized, and so on. And the answer is positive to all of such questions. There he was interested in other things, so he did everything by hand in the setting that he was interested in. But I hope to have enough time to tell you that doing these things canonically actually has some really spectacular applications. So here's the theorem. There is a universal Higgs field theta, here I'm a little bit optimistic. I should put the theta local system attached to G dual. Theta x tilde over x going to from F. Yeah, let me just write it concretely. I stop writing the subscripts. It's X everywhere. So there is a universal such thing which interpolates all of these things. So giving rise to all theta V by taking the composition that I described. So you have FV, then you go to G dual tensor FV. And then you can go via this map to FV tensor O omega 1 minus 1. This is induced by this map here. And you ask that this composition is just theta V. So basically, to each torsor, you can associate a universal Higgs field, which basically depends only on the Lie algebra of the group. with the property that it computes all Higgs bundles of all small sheaves that we are practically interested in practice. So this is a very powerful result, and this actually holds without this assumption of smallness. So this works for any x. But now, something that is really very useful. So this is actually formal. This is the good thing about this theorem, is that once you have this construction here, you just do it in one universal case, namely, you apply this construction to V equals C age LA for a given age. And there you realize that the sheaf FV, well, C age LA is an algebra. So when you tensor with O hat, this is still an algebra. So you have a sheaf which is an O hat algebra, and so the corresponding derivations will actually be, the corresponding endomorphisms will not only be O hat linear, but they will be O hat linear derivations of your algebra. Moreover, they will commute with the action of G, the left regular action of G on this thing. And so basically, they will just be given by elements in the Lie algebra tensor with O hat. And that's exactly what comes from this construction, because if you're thinking of this dually, it simply says that, so dually, you have a map from sen x tilde over x, which is the dual of omega 1 into G tensor O hat. So this theorem is saying you have to produce for each guy here, and basically for each tangent field, you have to produce some section of G tensor O hat, which kind of gives rise to all of these sen operators by using the action of the Lie algebra on V. But you just do it in one universal case, which is C age LA, and you observe that any locally analytic Banach representation will embed into a completed direct product or direct sum of such representations. And so once you do it for sufficiently many V's, you get it for all V's by functoriality. So this is already in Lue Pan, actually. And it's an extremely nice argument, because basically there is not much to do. The hard work is in there. So why is this useful? No, I'm saying that this is a universal guy. And it computes all the ones that I constructed before by using, moreover, the infinitesimal action of the Lie algebra on each representation. So any of those that I constructed before is just obtained from this one by composing with this natural map. Okay, so what are the great advantages of this sen x tilde over x is that it kills locally analytic vectors in O hat x tilde. So let's stay in the small setting with A tilde being the functions upstairs on the torsor. Then we saw that A tilde GLA, this is H0 pro et al. Of X, F applied to CLA of G. This was like one of the very first calculations I did before doing all this geometric business. But this you can also compute by saying that it's H0 of X tilde CLAG tensor with O hat, and then take invariance under G, because after all, X is just the quotient of X tilde by G. But this is nothing. Yeah, I mean, this is CLA G tensor with A tilde invariant under G. In other words, these are locally analytic functions from A tilde, from G into A tilde. Or you can also put A tilde G locally analytic if you want. But on the other hand, we can do the computation differently, because we saw that the cohomology here of the sheaf is computed by the cohomology of the Higgs field. So if you specialize this to I equals 0, you know that this is killed by this Sen operator. And then you use the fact that this Sen operator here is actually induced by this universal guy by using the action of the Lie algebra on V, which is just the left or right, I never remember, action on the group on its space of locally analytic functions. And then you unravel definitions. So there is some bookkeeping here. Bookkeeping, which is very confusing, but okay. Because you always have to choose between left and right, and obviously I'm not able to do this on the board. But you just stare at this formula and you kind of identify these things. You know that any such vector here will kind of land in the kernel of this Sen operator, and the kernel of this Sen operator is kind of deduced from the composition of these two maps, and then you deduce from here that any this one? Ah, this? Well, yeah, you can, because it's just the orbit map. So if I have a locally analytic vector there, it will automatically land into A tilde GLA. Yeah, so any V in A tilde GLA is killed by anything in the image of the Sen map. You see, this Sen guy creates derivations, I mean differential operators, which act on this space of locally analytic vectors. And the statement, once you unravel all these things by remembering that this is actually the transpose of this theta, so of course there is some duality involved here. But the key point to remember is that since locally analytic vectors there are actually killed by this theta v, anything that is in the image of the Sen operator will actually kill those locally analytic vectors. And so this is an extremely useful result, because if your Sen operator has big image, then you get that many differential operators are going to kill your locally analytic vectors. And so now obviously there is a question, how can you actually compute these Sen operators in arithmetic cases? Also, I want to add, so this is easy once you have all the previous results. Something which is not easy is the following thing. Still in the small setting, if this map theta is surjective, which will happen in the case of Shimura varieties for very non-trivial reasons, then actually the cohomology of this FCLA is concentrated in degree 0. But, well, I guess everyone is as tired as I am, or even more. At some moment, I was explaining that the computation of these cohomology groups is somewhat related to higher derived locally analytic vectors in A tilde, but not quite. This is really the case if X tilde is perfectoid. But for general Shimura varieties, you don't know that X tilde is perfectoid. So if you know that this is perfectoid, which is the case for modular curves, for instance, then you will deduce that the higher locally analytic vectors in A tilde vanish. So this plus previous discussion implies that if X tilde is affinoid perfectoid, then A tilde RGLA is equal to A tilde GLA. And this is one of the most difficult results in Lue Pan's first paper, that in the modular curve setting, this actually holds. But now this just follows from the general formalism. This no longer has anything to do with modular curves or things like this. You just compute, I mean, of course, you still have to compute the Sen operator for modular curves. Now I'm going to tell you what is the general result for Shimura varieties, and it will be surjective there, so you will have this general vanishing result. One of the great advantages of this theory is that since it is very canonical, you can always reduce computations to very concrete examples. And so you don't need to be in a general setting. Now, you just do local computations all the time. And of course, they are not easy, but still it's much easier than to be in the general setting of some Shimura variety where you don't know if you have to put some global input into the calculation or not. You just separate the two things. These are purely local statements, and then we're going to apply them to the case of Shimura varieties. Now, everyone knows that I'm a big expert in Shimura varieties. Who doesn't recognize the existence of any Shimura variety other than modular curves. So I guess I still want to do the general result. So we're going to take GX, a Shimura datum, but tomorrow we're going to get our hands dirty with the case of modular curves and do everything, make everything explicit. So we take a Shimura datum, but I'm going to assume, otherwise the notations are just terrible, with proper Shimura varieties. Plus technical hypothesis that experts know on the center of G. Basically, you don't want to have a non-trivial R-split torus, which is Q anisotropic. This is, okay, forget about it. So in this case, well, we have the reflex field, and we're going to fix an isomorphism with CP and fix L inside C, which is large enough to split the group, and such that there exists a Hodge co-character in mu in the conjugacy class defined by our Hermitian symmetric domain X, the conjugacy class defined by X, and which is defined over L. Okay, so starting with this, we get a flag variety, which I'm just going to base change directly to C. L is a, yeah, it's inside CP, and it's a finite extension. Yeah, finite. And so I have a flag variety, which is just the analytification of the algebraic one, where P is the parabolic of GL, classifying or maybe stabilizing the increasing mu filtration on each algebraic representation of G. So if I have an algebraic representation of G, since I have this co-character, I get an action of GM on that representation, so I get a decomposition by weights, and this gives me some increasing filtration, and these filtrations are parameterized by this flag variety. In the case of GL2, but unfortunately here it's not proper, but okay, everything I did extends to the non-proper case, so let's forget about this. But for GL2, this flag variety is nothing but the projective line, seen as an adic space. So, well, we have this flag variety, and we also have a tower of Shimura varieties. So fix a compact open subgroup Kp in G of the finite adels outside P, sufficiently small, and define S infinity, which is usually denoted SKP, to be the inverse limit of this SKP Kp. When I vary over all compact open subgroups Kp in the local group G of Qp. So this doesn't really make sense. Okay, I take an inverse limit of adic spaces, but still this makes sense in the Proetal site. That's what the Proetal site is devised for. of Sk for any given k, of time level k. And I'm just going to denote this by S, and this is a Proital torsor. Kp torsor. And this is essentially the main kind of interesting Proital torsors that we get in geometry, starting with towers of Shimura varieties, making them analytic. Oh, yeah, I forgot to say that this is really the algebraic Shimura variety tensored with C, and then I take the corresponding adic space. So I'm not really working with schemes here because I'm always in the setting of adic spaces. So I have to take my algebraic varieties, make them analytic. And so once I fix a finite level Shimura variety, if I increase the level only at P, I get this Kp torsor. And it's precisely here that I need this technical hypothesis about the center, because otherwise I have a quotient of Kp. But this is just technicalities. So this is a Proital torsor, and there is a natural question: what is the corresponding Sen operator in this case? Okay? And I introduced this flag variety. So there will be a miracle, namely that there is another map. So this is the natural map, but there will be a Hodge-Tate period map, which will not be really a map of spaces or anything, because I mean these are abstract things, right? This is just some object in the Proital site. But still it's a map of ringed spaces, ringed sites, from this into the flag variety with its structure sheaf. This is with the analytic topology. That I'm probably going to define tomorrow because this requires some work. But now, one of the great advantages is that, and this is Kp equivariant, that this flag variety has a lot of vector bundles, which are quite interesting on it. And what you can do is to take a vector bundle here and take its pullback there. And then you may ask, okay, maybe I can recover this way at least the omega 1 that appears in the definition of a Higgs field, this omega 1 twisted by -1. At least I would need to have some vector bundle here whose pullback gives me that thing. And so this theta will be induced by Hodge-Tate pullback of some surjection of vector bundles, will be a surjection of very explicit G equivariant vector bundles on the flag variety. Okay? So that's basically the general picture. You have your infinite level Shimura variety. It goes to the flag variety via some very non-trivial and very transcendental Hodge-Tate period map. And this Sen operator will be obtained just by taking two very explicit G equivariant vector bundles on the flag variety, one being a quotient of the other. And you pull them back here. And that will be essentially, so this, the pullback of this theta thing will be this guy here. So now I need to tell you what are these two vector bundles. So now there is an exercise that G equivariant vector bundles on the flag variety, these are the same as algebraic, finite dimensional representations of the parabolic you started with. Okay? This is just you take E and you take the fiber at the point 1, which is P mod P in the flag variety. And conversely, if you have a representation W, you can just do the usual thing, GL cross PW, and then you take the edification of this. So equivariant vector bundles on the flag variety are very simple. These are just algebraic representations of P. But now, this is really cool, because this P parameterizes precisely filtrations on algebraic representations. So if I take G, if I take V, an algebraic representation of G, I know that its mu filtration is P stable by definition of P. My P stabilizes all the filtrations on all algebraic representations. So if I take an algebraic representation of G and I restrict it to the parabolic, this will be just an increasing chain of representations of P. So this V has an increasing mu filtration FNV by P sub-representations. Okay, which I'm just going to do later on. But now I'm going to take a very specific V, which is just G with the adjoint action. That's an algebraic representation of my group. And what is the filtration with respect to P? Well, you have the parabolic Lie algebra, and there you have the Lie algebra of the unipotent radical of P, the nilpotent one. Okay? And this is P stable, and that is the filtration that you get from this mu, precisely because we are in the setting of Shimura varieties and mu is minuscule. Okay? So everything is kind of concentrated in between -1 and 1. So the filtration, the P filtration on this Lie algebra, seen as a representation of G, is just given by n inside P inside G. Now, by this construction, you get, let me call this EW, you get N0 inside P0 inside G0, but what is G0? This is nothing but G tensor with O flag. Because when W is really a representation of G, this really becomes W tensor with O flag. And so these are G equivariant vector bundles on the flag variety. Well, E1 goes to E2 is nothing but the dual of G0 surjecting onto the dual of N0. Okay? So you take this quotient of G equivariant vector bundles, you pull back via the Hodge state period map, and that will give you this thing here. And if you remember, where was it? Somewhere. I probably got rid of it. No, it's not there. So I was saying at some moment that the image of this Sen operator kills the local analytic vectors. Okay? So the image here will basically be N0 once you redualize everything. And so this plus the previous theorem implies that N0 kills the sheaf OLA, which is obtained by taking O hat, restricting to the topological space of S infinity, and taking KP analytic vectors. So one has to be careful because a priori this S infinity is not really an adic space in complete generality, but still it makes sense to look at this topological space. And there you can define a sheaf of locally analytic vectors with respect to the action of the group KP. And this sheaf is going to be killed by N0 precisely because we computed the Sen operator in this setting, and it's basically given by this M0 once you redualize everything. And so we obtained in this way that for a general Shimura variety, okay, maybe with some assumptions, but Camargo doesn't need them. This is just to simplify the exposition. For general Shimura varieties, this sheaf of locally analytic vectors is always killed by this sort of horizontal universal nilpotent subalgebra in G0. And so for G equals GL2, this was one of the amazing discoveries of Lue Pan. And actually, even before that, Berger and Colmez in dimension 0 proved something very similar to this. And this was actually Lue Pan's inspiration for all this business. So tomorrow we're going to make very explicit what happens for GL2, and this N0 will be a very explicit differential operator around each point. And so this will give rise to some very explicit differential equations that are satisfied by locally analytic vectors. And then we're going to impose some extra conditions to make them very small. Actually, it's not tomorrow, it's on Thursday. And so when we study these differential operators, this will just be some sort of undergrad class in solving PDEs with linear PDEs. And so from that, you can get a very good understanding of the structure of this sheaf. And this is very, very important because this sheaf is actually related to a lot of interesting things happening. So yeah, next time I'm going to try to explain what's the link between the cohomology of this sheaf and the completed cohomology of this S infinity, and then try to specialize to the case of modular curves and how this relates to the Drinfeld tower. Sorry?
Why does this give the same operator?
Oh, this is a deep theorem. This is one of the main theorems in Camargo's paper, but hopefully next time, if I have time, I will at least sketch what are the key ingredients. But this really relies on very deep results in p-adic-Hodge theory.
Okay, thank you very much, Gabriel, for this beautiful lecture. Are there questions?
So from there, what you wrote, can we get the surjectivity of the Sen operator, or for the?
Can we get what?
Surjectivity for the modular curve that you meant.
Well, I mean, for a modular curve, Lue just computed everything by hand, and he checked essentially by just looking at the formulas that this is surjective.
But can we do it right now?
Well, I mean, it's obvious, right? It's the dual of an embedding of vector bundles. So. And this stays surjective once you pull back here. And this is just descent along a torsor. So,
Other questions?
but I really want to insist that this thing actually works for arbitrary Shimura varieties. In particular, you don't even know that you have some universal abelian variety on top or anything like that. And you don't even know that that thing is perfectoid. So it's really kind of a miracle that is just group theory in the end. And the really amazing thing is that the computation of this Sen operator essentially comes down to doing what happens over C and transferring via some very hard comparison theorems in p-adic-Hodge theory. You do the computations over the complex numbers. There you have some Riemann-Hilbert correspondence over C. There is an amazing theorem of some people that I will mention next time, Liu, Lan, Diao, and Zhu, saying that what happens over C can be transferred over QP. And so then you do all these computations over QP by just taking the geometry over C and putting it here. That's why basically there is only group theory at the end.
Okay, so maybe there will be more questions in the Q&A session. Thank you very much, Gabriel.